Huh. Sorry, 1 second. There we go. Okay, and switch the view. Okay, so my name is Jonathan Byrne. I am head of the technology office of Intel Movidius. We are a hardware company. We develop a chip that does computer vision and can run deep neural networks. So today I'm going to be talking to you about machine learning. I'm not quite sure what level everyone's at, so this is a very high level discussion, no horrible equations or anything, but we'll give you an overview of the different kind of aspects of machine learning. So in this talk, I'm going to give a brief history of artificial intelligence, where the term comes from, where machine learning comes from, that as well. I'll then talk about data, because that's the most important thing in machine learning. And then I'm going to talk about 3 styles of algorithm: supervised, unsupervised, and reinforcement learning. So originally, I mean, people have been talking about thinking machines for hundreds, if not possibly thousands of years. But when this kind of kicked off was 1943. McCullough and Pitts came up with a mathematical model for neurons in the brain. And they showed that by presenting it with data, it could learn. This was really fleshed out then in 1950 by Alan Turing when he wrote his famous paper, Computing Machinery and Intelligence, where he coined the term machine intelligence. And he made a very nice argument as to whether machines could think, or, or were they just processing stuff. He's like, well, I don't know if you're thinking, for example, let's judge it based on behavior. If you get a chance, I strongly recommend you read that paper. Normally his papers are incredibly difficult to read, but that's a really interesting one. And he lays out, the Turing test. He also describes basically a very early version of genetic algorithms, and he describes neural networks. So even at that stage, he was outlining this sort of stuff. The actual term artificial intelligence was coined in 1956 by McCarthy and Norbert Wiener, who developed cybernetics and Lisp. And this was really where it was taking off. They were starting to see applications working, and they really thought that they were going to solve this very quickly. 1959, the actual term for machine learning was coined by Arthur Samuel. And in that sense, he was developing game playing programs, so tic-tac-toe and checkers. He was coding them up, and he kind of noticed that with like tic-tac-toe, noughts and crosses, you can just enumerate everything. With checkers, there was too much to enumerate, and instead you have to let the computer learn. So you have to program it in such a way that it can learn without being explicitly programmed for every sort of condition. And early on, this worked really, really well. They got a couple of early wins that were great. SHRDLU was one where they, defined a virtual environment, and they said, they started showing that it could reason. You could say, pick up the big red block and put it on the green triangle, and it would do that. They also started building these devices. So this was the Mark I perceptron, where they actually tried to wire up a neural network. And right from the earliest days, there was lots and lots of hype. So here we have a computer designed to read and grow wiser. And they expect that it will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence all fairly soon. But unfortunately, this didn't pay off. These early wins led to kind of an overconfidence, where they said, look, in 20 years' time, we're going to be able to do anything, work that a man can do, or within a generation, the problem of creating artificial intelligence will substantially be solved. And we are still working on that problem. So this overselling of it, when they actually started bringing it out of these very controlled situations, they found that it didn't work. They found that the problems that they thought were hard, they assumed that the problems computers would find hard are the same problems that humans find hard, like chess and complex mathematics. What they found out was actually, no, those problems are very easy to solve in a computer, but simple things like identifying a green block in an image, or walking, something that humans are very easily able to do, they were very hard for a computer. And all that hype and overselling meant that by 1974, it had hit its first AI winter. 10 years of funding, nothing really to show for it, so the funding dried up. This was the first but not the last of the AI winters. Again, around 1990, there was a massive growth in neural networks that kind of peaked and then troughed when they found out that they could only make networks up to a certain size before they kind of broke down and didn't work. And this is where they kind of rebranded it. At this point, after being burned twice, they stopped using the phrase artificial intelligence. Artificial intelligence comes with connotations of, a robot that you can debate Wittgenstein with over a game of backgammon while it makes you a nice cocktail. And that was not materializing. So they rebranded and they said, okay, here's what we're going to do. If you give us data, we're going to fit a line to that data. That's machine learning, okay? We're not going to say that it's going to be conscious. It's not going to be doing all this. It's not going to be reproducing itself or anything like that. We're just going to look at the data and we're going to extrapolate patterns out of it. Given a kind of high-level description, it's a field. You can think of it as a way of, computers, the ability to learn without being explicitly programmed, or to kind of simplify that something more is you can say that you have a function that is programmed via exposure to data. So you're not implementing the code. The data is weighting the code. Essentially, this is tying into analytics, that you're using historical data to make predictions, which has another name, which is basically statistics. That's being done by computers. So machine learning, despite its fancy name, is kind of a weird relationship between computer science and statistics that the mathematicians don't like because it's not quite as rigorous as they would expect. So there are many deep learning or machine learning algorithms out there. But I find the easiest way to split them is their style of learning. And their style is either supervised, unsupervised, or reinforcement, which I'll cover today, or their algorithmic similarity. So generally, they will be based on, for example, decision trees use decision tree tree data structure. Neural networks use a graph data structure. And you can basically cluster the algorithms by those approaches. But I think what would be of most use to you is to understand the styles of learning, because then you can see how each of these different approaches is using just one of these three styles to do its learning. And it splits into something like this, where you have your machine learning in the middle. You've got supervised learning, which falls into the task of classification or regression. Unsupervised learning, which is generally either clustering, dimensionality reduction, and then reinforcement learning, which is just a kind of one size fits all. So I'm going to cover all of these today and give you a sample of them. Now, before we do that, we need to talk about data. Data is what we're programming it with. Data is what we're using on the algorithm. So we need to understand some terminology about it. The data set that I like using is the Titanic data set, because you have a bit of an intuition as to what is important and what isn't important in the Titanic data set. So you've seen the movie, women and children to the lifeboats first. If you were poor, probably didn't do too good. They'd probably lock you in on the lower floors, So you can understand that each of these columns is a variable, and each one of these could have an impact. So the question we're going to ask is whether or not the person survived. Okay, so if we look at passenger ID, that's probably not going to have a huge amount of relevance. Passenger class could have a huge amount of relevance. The name, on its own, probably not, but you can probably deduce from the name whether they're male or female, which would have an impact on it. And well, we've got in the next row, we've got the sex here. So, that information's already in it. So these are probably redundant. You have the age, whether they're parents, their siblings, how many were on it. The ticket number, probably not that important. The fare, which, again, it's going to tie into the class. So it'll give you an idea on that. So these are all attributes of the data set. Now, to simplify this so that we can look at it, we're going to just take three of them. So we're going to have our passenger class, the age, and the sex, and whether they survived or not. Okay. Now, why am I choosing three? Because humans can visualize in 2 or 3 dimensions, but when we go to 4 dimensions, it gets a little trickier. Which brings me to the next thing that you're going to hear a lot of in machine learning is the n-dimensional feature vector, which is a really fancy way of saying a row of numbers. That's all it is. So every time in deep learning, they like throwing this around. It makes them sound very smart and intelligent. All it is a row of numbers, okay? So here we have our three-dimensional feature vector. So we've taken the values, we've turned them into numbers. We've got 1, 2, 3, they were already classes. Sex we're going to set to 0 or 1, and age 0 to 100. So this is our feature vector row of numbers for an individual. Now we can plot them out on our three axes. We have age here, sex here, class here. And then we can start looking at the data. Okay, let's see whether someone survived. So this is what we call a label. Okay, so we have these three, and then our label here survived. And we're going to color in the graph based on that label. And what you can see very quickly is these different clusters, red means dead, green means alive, they fared quite differently. Okay, so up here we have first class females of all ages did very well. Second class did okay. Third class, not so good. And then we have here, now there's certainly more males dead, but there's still a lot of green in there. So first class males, certainly the younger or older survived there. Whereas the second class, only the younger ones survived. And then the third class, only some of the younger ones survived. And this basically gives us a function. So you can say, okay, if I have the class, sex, and age, can I predict whether they survived or not? And yeah, you can work out fairly quickly which cluster they're in and work out the odds. Now, there's nothing special about that label. Okay, it's just another row, or sorry, another column in the database. You could switch it around. You could say, okay, well, if I had the class, whether they survived or not, or the age, can I work out what gender they are? And you can do that as well. Okay, so nothing special about the labeled data. You can use any of them to find the other ones. And this is called supervised learning. Supervised learning is where you have a function that tries to map data X to a label Y. So function X will give you Y. Exactly like we were showing there, if we have our age, sex, and class, can we work out whether the person survived? And what we're doing is basically function approximation. That's what the data is doing. It's coming up with a way to map this out. If you put these three inputs in, it'll spit out a value. And this, with supervised learning, you always require a label. You need labeled data that is the target output. Okay, so this is a method that we're going to cover now. This is very much a statistics based approach that was then moved onto computers, called linear regression, also known as fitting a line to the data. And we have our house price here, that's our target, our label, and then our house size, the data. And we're going to come up with a function, a line, that was going to explain to us this data. So here we have our data. How do we find a line that fits this best? Well, what they use is a method called linear least squares. You basically fit a line to the data, and then you compute the distance of all the points to that line. You add up all those distances, and that is your error, also known as a residual. And once you have that error value, you can then use a technique to minimize that error value. And it will move the line. And then you move the line, you recompute the error, and then you move the line again, and you keep doing this until you've minimized the error. So this technique, which underpins a huge amount of techniques in machine learning, is called gradient descent. So, for example, neural networks use backpropagation to train. It's basically gradient descent. It's an optimization technique. So here's how to imagine it. You're stranded on the side of a mountain, and there's a thick fog. You can only see 3 foot around you, and you need to get down to the bottom of the mountain. What do you do? Well, you haven't got much of a choice. You can only see 3 foot. You look around that 3 foot, and you go, okay, there is a slight decline over this direction. Let's walk that way. So you take a couple of steps, and then you use your technique again. You look around you, you find which is the one that's angled downwards the most, and you walk down that way. And eventually, if you keep doing this, you hope you will get to the bottom of the mountain. And while kind of true, you can end up in things called local optima. So if your mountain is like this and you're lost in the fog, you don't know whether you're here or over here. You know, have you really got to the bottom, or are you just stuck in one of these local valleys? But this technique is what's being used here to compute this line and to move the line based on the error to minimize the error. And once you have this, you can use it as a predictor. So now we have a house size that's not one of these data points. We fire it into this line, the line hits here, and then it goes, that house, a house of that size should have this price, which is a useful thing. Now you can use it for predictions. So this technique, linear least squares, it's a supervised learning technique, label data. You're minimizing the error over all the points. It's useful for simple predictions, but you get caught in these local optima because of this gradient descent technique. What do I mean by local optima? What does a local optima look like? Well, if we have noisy data like this, where we've got these red outliers, which is basically like every bit of data in the world, you'll always have some noise. If you try and use this, you're going to end up with this line here, which, you know, we can see visually that that's not really fitting our data. So instead, computer scientists come up with a very computer sciencey technique because it's lazy and stupid and minimal effort. And instead, we let the computer do all the work. So it's called random sample consensus. Basically, we're going to pick 2 points because that's what you need to draw a line, and we're going to draw a line. And then once we've drawn that line, we're going to set a threshold on either side of that line, and we're going to count how many points fall within that. So this line here has a score of 4. Now, because that's not a very good solution, we're just going to do it again. Randomly pick 2 points, draw a line, count how many are in. Okay, that scores 4. Do it again. Okay, this one does a bit better. Now we're up at 7. And we just keep doing that again and again and again. That's why the mathematicians don't like this stuff, because they're like, well, you're just randomly sampling, really, aren't you? But this is shown to be a very good technique that is incredibly resilient to noise. So just by picking random points, drawing the line and counting it, eventually, if you iterate enough, you're going to get a really good answer. The way to think about this is, rather than the gradient descent approach where you pick a point and you're optimizing that answer, instead you're randomly sampling from the search space, which is the equivalent of like little guys being dropped in on parachute, and then when they hit the ground, they will radio back their altitude. Okay, so that's a nice way of visualizing this, that they're sampling the space rather than optimizing the particular solution. And in this case, it gets way better answers. One last technique is k nearest neighbors. All the k means, that always confused me. Basically means you manually have to pick the number of neighbors that you're going to use whenever you see k. Just you manually have to pick the value. So today we're going to do 4 nearest neighbors. So we have a bunch of red stars and a bunch of green stars. And then we get a new data point. Is it a green star or is it a red star? Well, we're going to look at our 4 nearest neighbors. 3 of them are green, 1 of them is red. So it's going to be green. Let's take another one. Now, here we have it. We're going to look at the 4 nearest neighbors. 3 of them are red, 1 of them is green. We're going to make it red. Very, very simple technique, but this is used everywhere. Like in your Spotify playlists, in your Google, YouTube recommendation algorithms. If you click on videos, then these are the videos I like. It will find you other videos similar to that. It's using an approach similar to this. So supervised learning requires labeled data, which means you have to have a target. Doesn't necessarily have to be complicated. I don't know if you'd consider k nearest neighbors learning in the traditional sense, but it's a technique that will allow you to mine the data, and it's a very powerful tool for interrogating the data. It allows you to ask questions. If I've got A, B, C, what's D? Breaking it down, lots of things fall under supervised learning, decision trees, support vector machines, neural networks, they're all in here. So the other one, unsupervised learning. This is a much simpler technique because we have no labels, just the data. We're not going to have a target function. We just want to look at the data, and normally it's used for 2 things, clustering or data simplification. They're generally simpler methods. They do not require any labeled data. So you could, instead of having to have a bunch of pictures and have them labeled cat, dog, fish, or whatever, you could just give it a bunch of pictures and it'll group them based on similarity. May not need training as well. So you can generally run these out of the box. An example of this is means clustering. Again, K means that you have to know the number of clusters in advance, which we're just going to do by eyeballing today. But basically, we're going to use this algorithm to group similar data points together. And this is very useful if you're trying to discover underlying patterns. It's, again, a computer science technique because it just basically guesses and then hacks around and runs it 50,000 times to get the right answer. So here's how it works. We're going to pick the number of clusters, K. We're going to just randomly assign those points out as centroids. Then we assign all the points to the closest centroid. We then recompute the centroids for the newly formed clusters, and we just keep repeating this process. So what does this look like? Here we have a bunch of data, and just from eyeballing it, I'm going to say there's 3 clusters. So we randomly throw down a centroid, which is going to be like, this is the center of our cluster. And of course, it's in completely the wrong place. But what we do is we compute the distance from for each point to each of these clusters, and then whichever one it belongs to, whichever one it's closest to, we're going to assign it to that one. Okay, so this, again, still isn't looking like a very good answer because we've got all these greens up here. This orange one has got like this cluster and bits of this cluster and bits of this cluster. What do we do? Well, once you've computed this and which ones they belong to, we're going to take the average of all of these points and move the centroid there. And then what we do is we recompute all the distances again. And now it's looking a little more clustery. So this green has moved down here, this blue is moving over here, the orange is moving over here, and the points look like they're belonging to the right cluster now. And we just repeat the process again, find the average, move the centroid, compute the distances, and just keep repeating that again and again and again until the centroids stop moving, and then we're happy. Okay. The other technique that can be done in an unsupervised way is dimensionality reduction, flattening the data. So think back to the Titanic data set. We had 9 dimensions on the data, but some of them weren't really useful. Like the passenger ID wasn't useful. The ticket number wasn't useful. And if we could maybe get those 9 dimensions down to 3 dimensions, then you could actually visualize it and look at it, which might be a lot more useful. But how do we know which dimensions to throw away if we don't know in advance? So you can use, let's just look at the data here. So here we have 3 axes, our X, our Y, and our Z. And we have a bunch of data points lined up around those. So the first thing we can do is just take an axis and look at it and go, okay, well, there's a lot of overlap here. Okay, there's one distinct cluster over there. So maybe the X-axis might be useful. If we look at the Y-axis, these are very clearly separated. There's lots and lots of variance here. And if we take the Z-axis, again, we can very clearly see that the points are separated out and distributed. So what principal component analysis does is it will take this data and it will fit a plane to it, or a hyperplane if you're looking at more dimensions, and flatten it down. So how it does this is it basically analyzes the variance over all the axes. It finds the one that has the most variance and uses that value to align the plane. If you want to look under the hood, I'll link to the presentation. The link below will explain it in more detail. It's computing eigenvalues, which represent the variance, and then you compute the eigenvector, and then you can collapse it down. But the principle here is that it will take your data and allow you to remove variables that are not really having an impact on the data. So there's far fewer of these techniques. They mainly fall into clustering or dimension reduction, although there's lots of stuff. There's lots of techniques now for dimension reduction being used, and clustering as well. But yeah, basically that's what you can do. It's a more robust technique, but there's less you can do without it. So supervised will allow you to interrogate the data, but it requires a target label. Unsupervised can cluster and simplify the data, and it doesn't need a target label. Now, the final one, reinforcement learning, my favorite. This is kind of different from the other two. It's when you're dealing with a problem where the environment is known, but there is no deterministic solution is available. How can you know the environment but not have a deterministic solution? I will explain in a minute. It's stochastic. So this is not an entirely random algorithm, but it's not deterministic. Okay, so it essentially means you could run it 10 times and you might get slightly different answers. It's not following a set of a fully deterministic set of rules. What's nice about these techniques, though, is you tell it what to do, but not how to do it. That I'll explain later. And it's a trade-off between optimization and exploration. It's not just optimizing, it's also that randomness allows it to explore different possible answers. So how do problems get unsolvable? If we understand the whole environment, how can it be unsolvable? Surely, if we understand the whole environment, it's just a matter of enumerating through everything. But if you had a problem where you had 100 switches, switch being either on or off, how many possible combinations are there? It's 2 to the 100, which is an exponential increase. Okay, so to get your head around this, a lot of people, they see this graph and they think, okay, this is going up pretty fast. This is exponential. But you don't realize that where this graph ends, it gets insanely steep. Okay, so I'll try and explain this with a problem that is the same as the 100 light switches. Each time you're adding a switch, you're doubling the number of solutions, okay? And what we could visualize this as is, if you take a piece of paper and fold it in half, how many times would you have to fold it over to get to the moon? 1,000,000 times? 1,000 times? 100 times? So each time you're folding it, and I know you can only fold a piece of paper 7 times, but imagine that we can keep folding it. Each time you fold it, you're doubling it. So we're starting at 100 microns thick, the thickness of a human hair, and we keep doubling it. How long does it take to get to the moon? Well, 30 folds will get you to 100 kilometers high. 42 folds will get you to 439 kilometers, which is about the same distance as the moon. 81 folds will get you 127,786 light years, which is bigger than the Milky Way. And if we just round it up a bit and go for 103 folds, that stack of paper is now 93 billion light years tall, which is the equivalent width of the observable universe. In under 100 folds, you go from 100 microns, or sorry, just over 100 folds, you go from 100 microns to the width of the observable universe. That's how big exponential gets. These type of problems that can be solved are called, and they can be solved by these stochastic solvers, okay? The type of problem is called a non-deterministic polynomial problem, to make things sound very complicated. All that means is that the solution can be tested in polytime, which means you can, if you come up with an answer, it may not be the best answer, but you can check it very quickly. But again, there's so many possible answers that it could take a long time to find the best one. So how do you tell it what to do, but not how to do it? And the easiest way I have for visualizing this is the hot and cold game. So you have a kid who's blindfolded and he's trying to find the present. Now he's going to just walk in a random direction, but you can give him some feedback. You can say he's getting hotter. Okay, you're not telling him a direction, you're just telling him that he's getting closer. Or if he goes too far, he's getting colder and he'll change direction. And that sort of feedback basically pushes him towards the correct answer. This type of random, directed randomness means that you have a nice balance between optimization versus exploration. So you're not just randomly guessing, you are randomly guessing, but optimizing those random guesses. So let's see this in action. We're going to look at the infinite monkey theorem. So if an infinite number of monkeys randomly hit keys in a typewriter for an infinite amount of time, they would almost surely write the complete works of Shakespeare. Sounds good. And yes, that is technically correct if you had an infinite number and an infinite amount of time. But let's actually work out how long this could take. Let's type to be or not to be, that is the question. And we're going to just assume this is a keyboard with lowercase letters, no uppercase, no fancy things. And we're going to say 27. So the odds of them hitting T is 1/27. the odds of them typing T0 or TO is 1 in 729. And the probability of typing the entire phrase is 1 over 27 to the power of 39, which is this insanely large number. To give you an idea of how big that number is, if we had a computer that processed 1 million combinations a second, it would take this many years for it to go through every single possible solution. Or, to put that in perspective, this is the age of the universe. So many, 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 many times over the length of the universe to solve this problem. There's just too many combinations. So here's our solution. We're going to use a thing called an evolutionary algorithm. This is a reinforcement learning technique that is inspired by biological evolution. When I say inspired, I mean inspired. It's nothing really to do with evolution. It's a very simplified 1950s idea of evolution, but it gives you a nice metaphor to understand what's going on. Okay, so it's heuristic. It's a stochastic solver. It may not find the right answer, but the alternative is to brute force it, and we don't have the time for that. So here's how it works. We randomly generate some solutions, pure random. We then evaluate those solutions with a fitness function. In this case, we're going to check how many letters are in the right place. We're going to select the best solutions, so only the ones that have the most right letters in the right place. We're going to take those. We're going to use them. We're going to combine them together to make new ones, and then we're going to throw in a bit of mutation to kind of mix things up a bit and make it a bit more random. So here we have a target phrase, that, and we're going to just randomly make a couple of answers. These are individuals. And this one gets a score of 1 because the T is in the right place. This one gets a score of 2 because there's 2 letters in the right place. This one gets a score of 2, 2 letters in the right place. Fully randomly initialized, just guessed. We're then going to cross them over. So we're going to take the 2 parents that did very well, and we're going to cut them in half and recombine them. And that may get you the right answer, but also it may not. Okay, you're essentially just cutting 2 bits and sticking it together. And the final step is we're going to introduce a bit of mutation where we just take a good individual and we'll just change a letter on it. So let me see if I can show you an example of this. Okay. So can you see the screen here? Yeah, okay, good. So how long do you think it will take to solve a problem that takes many, many, many times over the length of the universe? Okay, have a guess, and here we go. This is why it's stochastic. It's stuck. It can't get that last one. Hey, there we go. That was about 20 seconds. Let's try it again. So normally this takes around 10 seconds. Can we do it without the crossover? Yep. Crossover is a nice feature, but you can actually just do it with mutation. So take good answers and then just change random pieces and keep them if they're better, or throw them away if they're worse. And eventually it'll just kind of get the answer back there. And yeah, so that's about 12 seconds. So on average, with crossover, you get about 8 seconds. Without crossover, you get about 12 seconds. Okay. Oh, actually, while I'm here, let's. Okay, can you see this? So we can also use this to do other things, not just solve infinite monkey theorems. You can use it to design cars, where you generate a bunch of random answers, keep the ones that go the furthest, and cut them up and use them to make new designs. This is great fun. I really like these algorithms because you can just run them, kick them off on a Friday, you come in on a Monday going, what the hell has it come up with? Really nice. So back here. Okay, and switch. So this is actually used for design applications. Design is an open problem. There is a fixed number of designs, but like to actually find the optimal one is really hard. This is the Shinkansen train in Japan. This was the original nose cone, and as you can see, developed clearly by an engineer. Nice and straight, boring. And then this is the one that was developed by the evolutionary algorithm. And then this was one that was even further optimized. Very kind of novel solutions to these sort of problems. They also used it for optimizing fiber optic cable. Again, engineering solution, make it all very uniform. But they found that by varying the size and position of the holes, they could actually send more information down it. And again, this was being telling it what to do, not how to do it. Gets really interesting though is when it uses things in a way that just humans do not expect. And one example of this is this paper in 97, where they tried to evolve a circuit. They used a field programmable gate array, which is an FPGA. Basically, it's a programmable chip, and they wanted it to recognize two inputs. So one thing they did do is normally you have a clock pulse that tracks everything on the chip and makes sure everything moves in lockstep. But this time they didn't. They just got rid of it and said, kicked off the, solve the problem. Can you recognize these two distinct inputs? About 4,100 generations later, they could. And they came out with this, a mess of feedback loops. In an effort to understand it, they started removing parts of it that were not connected. But they soon found out that they couldn't, there were some parts that weren't connected at all, but they couldn't remove them. So even though that they had presented them with this chip with the intention of it using Boolean logic to solve the problem, it actually used the inherent components of the chip to basically solve it through feedback loops and electromagnetic interference, which is a pretty novel solution. Another guy in the early 90s was using it to evolve robot locomotion. So he'd basically build a virtual world and would allow the guys to, the robot, basically the creatures. I don't actually know if you can hear this. I'll just talk through it. But yeah, he wanted them to evolve different ways of moving. And what he found was they started coming up with really clever ways where they didn't even like move their arms. They just went really tall and fell over as a way of moving. Again, you tell it, move as far as possible. You didn't tell it how to do it. This, of course, has lots of applications in computer games. This is one I did because I played this game called Tori Bash. I literally could not play it. It was too complicated. But I knew that I could basically get the genetic algorithm to do it and solve it based on the score. I was able to come up with these very, very complex moves just based on the score as feedback. And where you're seeing this in computer games now is like animating different characters is really difficult. It takes a lot of time. And in computer games like GTA, they used to do it procedurally. So it would just, no matter what happened, they would act the same way. Now they're using these sort of algorithms to optimize. You give it a structure, a set of limbs, and you let it learn how to walk, which is a very effective way of doing it. So there's actually, I think there's a real nice bit here. Yeah, so you can come up with all sorts of crazy animations or configurations of the body, and eventually, just over time, it'll learn how to do it and move. Here's an interesting one. As it was training to move faster, it learned how to hop. So this was not explicitly programmed into it, but it realized that the configuration of the body to get that high speed, you could hop. And you can make them very robust to hits. And this, I think, is just kind of mean. This is when the AI rises up to get us. Douche, yeah. Anyway, great fun. So the other type of reinforcement, when people are talking about reinforcement learning, evolutionary algorithms are the kind of, you have to wait until the end before you can evaluate the individual. Reinforcement learning adds in a kind of reward during the process. So again, if you judged someone based on everything at the end of their life, that may be a bit unfair. Maybe they were doing some good stuff in between that you're not seeing, and you should be able to reinforce that. And that's what reinforcement learning does, is instead of creating an individual, evaluating it right at the very end, evaluate it while it's in operation. So here's a nice example of learning to park a car. So the AI starts off as random, has no idea, doesn't even know what the inputs mean or what they do. But during the course, so as it's driving around, if it bumps into something, you're going to penalize it. If it, uses the sensor information and manages to get closer to the spot, it's going to be rewarded. And you let it run several thousand times. And eventually it gets a little bit better. And then, yeah, still terrible. A lot of these things have to be done in a virtual world. The reason being is you have to do an insane amount of evaluations that if you're trying to do it in real time, it's really hard. So we're 30,000 evaluations in, and it's parking about as well as my mum. Okay, there we go. Yeah. But the nice thing about these reinforcement algorithms is they've been shown to, they can handle unseen environments that you haven't exposed them to explicitly. So there's a lot of kind of self-driving cars that are trying to use this approach. And when they get it, they get really good. So here, 200,000 evaluations in, and now it can park the car. These are used a lot in game AI now. They've shown that this approach is really good, and like all of the Atari games can now. That was a big challenge trying to, take all the Atari 2600 games, and they came up with an AI that could solve all of them. It could learn how to play each of them without having to be explicitly programmed for each of them. And where it's really kicking off is robotics. They're now using these approaches to not just do stuff in a virtual world, but then they'll train it in a virtual world and then bring it into the real world and then finish off the training there. So it has a good idea of what it can do. And this was part of OpenAI, where they actually, that's almost scary, seeing it learn how to do this, not just solve the Rubik's Cube, but manipulate it with its hand. And this is where robotics is going, using this reinforcement learning to learn this sort of thing. So that's it for reinforcement learning. You got Markov chain, evolutionary, a load of Q learning, genetic algorithms, that sort of thing. Just to kind of finish up on this, now if you're looking into machine learning, there's many different types. And if you're looking at the types, it's generally based on the underlying architecture, whether they're using an evolutionary algorithm, which is based on the evolutionary metaphor, or decision tree, where they're going to use trees, or a Bayesian approach, where they're using a Bayesian mathematics model. But they essentially, you'll have lots of variation, but underneath the hood, they're going to be using either supervised, unsupervised, or reinforcement learning. So that should help you get an understanding of how they're learning once you have an understanding of the type. So that's pretty much it. History of AI and machine learning, taxonomy of the different techniques, and I covered the styles of learning. So any questions on that?
I think that was great. And if anybody has any questions, they can just unmute themselves and talk, or they can just put it in the chat.
I'll be the first one to talk, I guess. My question would be, in the parking algorithm, the algorithm had to do 50,002 times to get into the right parking spot. But every time on those attempts, there's actually a mistake place that a mistake can happen. Also, if we change the parking spot, it will need to rearrange itself again. So how can it be adaptive in that sense that it doesn't fail actually every time we change the parking slot?
Well, okay, so that's a really good question. With that, you can change the parking spot, and because the metric is the distance to the parking spot, plus it has the sensor information, it introduces a flexibility. You can move the target. And so long as the problem stays relatively the same, it will work. Okay, so you can move the parking spot, but it still has the fitness, which is my distance from the parking spot, and the sensors. So using that information, it can maneuver to another parking spot. But as you said, if you change the problem radically, for example, in the Atari 2600 problem, where you have like a completely different type of game with different sets of rules, it basically has to start from scratch. There's a problem with these techniques called catastrophic forgetfulness, where you optimize it to come up with a solution to one problem. And then when you move the goalposts, it essentially has to unlearn what it has learned and relearn again. And what you find is it's easier to just start with a random new network. And that is, yeah, very much a problem with these sort of solutions. Yeah, sorry.
Sorry, please continue. Please continue.
But yeah, this is a very much a solution with any of these reinforcement learning techniques, is they will only learn based on the data that they have or the model that they have. And catastrophic forgetfulness is a huge problem. One technique is to use ensemble methods where you have multiple methods trained up. But yeah, very much an open problem.
Yeah, thank you so much.
You're muted, Serby.
I didn't realize this happened so many times. We have another question by Rajit, and he says that, would you have any comments on semi-supervised learning and how Google Photos works and lets you label some photos or people with other similar faces on its own?
Supervised. I have to remind myself. There's so many bloody things. Oh yeah. Okay. Yeah. So you train it with a small amount, and then you have a huge amount of unlabeled data. This is one of these techniques. So if you're training a deep learning algorithm, you can do this thing. So labeling the data, taking your 20,000 images or whatever and trying to label all of them is a bit of a pain, because it takes, I label about 500 images an hour if I'm paying attention and really going fast. And to do 20,000 is going to take a long time. So one hack that you can use is you basically label 500, you train a network on the 500, you then use that network to label the remaining 19,500 images, and then you train a model on that. And that kind of works. I don't know why it works, but yeah, it means that you can kind of bootstrap yourself. So this approach has been shown to work, and on particular data sets, it works quite well, and it's a very good hack to get your model ramped up. But it does have problems. If you are not supervising the label, it can end up overfitting based on whatever sample you've given it. So the semi-supervised approach is definitely good, and it allows you to get a lot more with just like a small amount of labeled data. But it has been shown to overfit in certain situations where it's making assumptions based on the limited amount of data that it's then using on the other unlabeled data. Okay, does that answer it? Sorry, I'll actually see if I can see the comments.
Can I have a question based on the Google Photos algorithm, actually?
What on the Google Photos algorithm?
Basically, last year I wrote an essay about how algorithmic bias is working, and when I was making a research, I came up with this article where it said Google Photos in 2014 or 15 identified 2 black men as gorillas because the training set was not trained well enough.
Yes.
So with the unsupervised training sets, to prevent any sort of like errors like this, is there like another validation or verification method that could be done, or is it just down to developing the data set over time?
So this is really, again, yeah, this is a huge problem. Okay, a lot of these algorithms, that 2015 data set problem was a problem because this is developed by primarily white, middle-aged men in Silicon Valley. Okay, and they get the data set to work for them and no one else. Okay, people talk about algorithmic bias, but it's not a bias in the algorithm. The algorithm just learns the data. It is the data that is biased. Okay, now let's just say, I'll give you an example. Okay, in Ireland, we want to write an algorithm that's going to find criminals. Okay, we have 200 years worth of data. So this should be easy. We'll just train it on all of that data. And one of the things this algorithm, it comes back to us, it goes, okay, if you're homosexual, you're a criminal, because That was against the law up until 1990 in Ireland. Okay, and you're like, oh shit. Oh, okay, okay. Now, why? Because the data, everyone just goes the data as if it's like just random numbers. That data was collected by humans. It was biased by humans. Those humans were doing things, based on their opinions. Okay, so it's that their biases are implicitly in that data. Okay, now you say, perfect. Well, we know that now. What we're going to do is we're going to remove that variable. We'll take that out. That's solved the problem, hasn't it? Well, actually, no, because there's stuff that is underrepresented in the data, where they are, for example, if we're doing the criminal thing again, spousal abuse was a huge problem in 1950s Ireland and was massively underreported. And that's not going to be in the data. So now you've got something that is not in the data and the algorithm will not pick up on it because it's learning. If you train an algorithm on racist, sexist data, it's going to end up being a racist, sexist algorithm. Amazon spent a huge amount of effort trying to come up with an AI to do recruitment, okay, for its engineers. And what they found was it would just reject women out of the bat, like just immediately, poof. And those Amazon guys, they know their deep learning, okay? They spent 2 years trying to fix it before they just threw it in the bin. Because the historical data is men do coding, which is completely untrue. Okay, so this data, this bias is implicit and people kind of trust the algorithm in some way. If you train it on racist bias data, you will end up with an algorithm and there's no way to deal with the unknown unknowns. I discussed this with Intel Legal because we've banned our facial recognition code, which is great. And because of how it was being used. But they were like, how do we get the bias in the data? And they showed me a data set, but it had no people with red hair in it because they were thinking in America, you show me a data set, I'll find something that's missing from it, and that's the kind of thing. So you can never really get rid of the bias. You just have to notice that it is biased and you have to understand that and make sure that you're not making any serious judgment calls if it's going to be, doing that. Yeah, in the States, there was an algorithm that was essentially arresting people based on, where they were and, what color their skin was. And they're like, oh yeah, but the algorithm told us, and you're like, Jesus, Anyway, so yeah, big problem, huge problem is the data that you train on.
Did seeing the algorithm reject women really quickly, did it help them sort of realize that it's not actually fair to do so?
Yeah, well, I mean, they initially tried to fix it. They tried to change the weighting so that it would weight on that less. And even then, it was still doing this. And they just threw the algorithm out. Because again, what you're doing here is you're asking it to learn from historical data. Okay, so you're saying, can we use the past to predict the future? And that's not necessarily a good idea. Past data does not necessarily have the key to the future in it. This is 2008 crisis. There was lots of algorithms out there. They didn't see it coming, the white swan or the black swan kind of thing. So there is very much limitations to machine learning and mining data for these sort of things. And yeah, if you do it with historically sexist data, you're going to end up with a sexist algorithm. So yeah.
Yeah, I think if you have any other questions, we can just have them as well.
Sure. Yeah, and also if you want to follow up later, just send Serby a note, and I will share the presentation as well if you want to go through that.
Yeah, and we put this on YouTube as well, so everybody will have access to the session. And tomorrow we will have a workshop so that you can get some hands-on idea of how you can build a simple image classifier. So that will also be fun to just implement theory into practice. I know it was like a lot of theory, which would be new to a lot of people, and it's hard to grasp everything in one go. So we can take it step by step and move into more detailed sessions in the future. So if it's anything is unclear, you can just send me an email or send Jonathan an email, and we can clarify it that way. But thank you so much for coming, and Yeah, Sam, do you have anything to say there?
Yeah, I just had one question for Jonathan, but I also just want to say thanks a lot for the presentation. It was excellent. So I just had one. So obviously there's a lot of applications for deep learning and machine learning. What do you think is the most surprisingly effective application that you've come across of machine learning?
Oh, that's a tough one. Like the thing that we're doing now, classification. You're going to sit down tomorrow and write a classifier. Okay, you showed a picture of a cat, and it will say that's a cat. Okay, that in 2012 was considered impossible. I was going to take 50 years. Okay, so the past 10 years has been working in computer vision. I can't narrow it down to one specific one specific application, because computer vision has just been used everywhere. And I mean, we're using it. We were on the DJI drones doing collision avoidance and stuff like that. That's where our chip kind of started out. But we're using it internally in the fab, in the factory, in leak slip. There's so many sources of images that we can just use this technique. And the classifier, I hope Tejas explains this as well tomorrow, ties into the object detector, ties into, they're all built upon this classification approach. But you show an image and it basically goes that you can find all the bikes, people, umbrellas, monitors. Like that 8 years ago was not considered possible. And now we've got a very, very, very robust techniques that we're using everywhere. And, you can use it on your phone. So it's not even requiring massive amounts of hardware, So that to me is really, really amazing. It makes this really fun, that you can use these deep learning techniques and they're getting so simple and mainstream that you can just use them absolutely everywhere.
Yep. Sorry, I wanted to ask, when is the tomorrow's session?
Oh, it's at 12 p.m. as well, so it's the same time as today.
Thank you.
It's going to be an hour-long workshop.
Thank you very much.
You can invite for that as well if you check. I mean, if you don't have the invite, you can just let me know and I'll send you the invite.
Yeah, I don't think I have the invite, so.
I'll send you the invite for that. You can just send me an email just after the session and I'll make sure that you have the invite for that session.
Oh, wait, what? Oh, where do I send you an email? I don't know your email.
Just a second.
Oh yeah, post that, Serby. That would be.
I was expecting that anybody who joins today's session would probably have emails from me, but probably it's just the link was everywhere, so maybe.
I couldn't find the link, so I just asked in one of the Discords, and then someone gave me the link.
Okay, so yeah.
I hope you don't mind.
Oh, no, that's absolutely fine. I just put my email in the chat box.
So where would it be by default? Where would the link be?
The link would be basically I'm sending email invites to everybody. So I had a Google sign up form for this event. So anybody who signed up, I send the link to them. But maybe the link was kind of advertised in a way that it was open to all. So that is why some people didn't receive the email invite. So I will send the email invite to you, and the link, basically the marketing.
Oh, it was in the NetSoc.
So the event is with GirlScript, NetSoc, and DataSoc. It was advertised through all the streams. So I will send the link to everybody who attended this session as well, so that they have the link as well. But I'll send the link in this chat also, just so if there are any problems, you can still access it. It's going to happen at 12 p.m. British summertime, Irish time, tomorrow. So this is the link for tomorrow's event.
So at 1 p.m. I'll better finish up.
Thank you so much, Jonathan. It was really good. And every session by Jonathan is so good because he's answering all the questions and everything. And I feel that he's very inspirational. He was my manager as well. And he's always so helpful. So thank you so much, Jonathan, for everything.
No problem. I got roped into another 2 talks next month in UCD. So I'll be giving one for NetSoc, I think I'm going to do image signal processing, which is basically how light comes into a camera and gets turned into an image. And I'm also going to do how to simulate a brain on a graphics card for a tech talk, I think it is. Anyways, so yeah, if you want to come along to those as well, that would be great.
I'll definitely advertise the links for those as well. So everybody who is attending these sessions would love to go and attend those, and we'll put this up on YouTube as well. So,
okay, take care, guys. See you. Bye-bye.
Bye.
Thank you.